Trane controllers through the ages.
Trane began in the era of electromechanical control, where units were driven by relay logic, contactors, and thermostats. This was the foundation of HVAC, but it lacked the intelligence, communication, and ability to meet the growing demand for automated control and energy conservation that electromechanical controls could not provide. In the 1980s, Trane's first step into digital central control and building automation came with the Tracer100. For its time, the Tracer100 was a breakthrough, allowing operators to schedule equipment, monitor performance, and acknowledge alarms. But it had clear limitations. There were no graphics, only text screens, and later versions offered a very limited ASCII-style visual. Functional and forward-thinking, yes, but still far from the integrated graphical systems that would follow. If you connected through a PC, the operator ran software on MS-DOS, or Microsoft Disk Operating System, the text-based platform that predated Windows. At the controller itself, technicians could plug directly into the controller's terminal port and view status or make adjustments through a simple text interface generated by the board's own firmware. Trane's introduction into full unit direct digital control, or DDC, began with the TIM, or Tracer Integration Module. The TIM directly controlled Trane units through a structured set of inputs and outputs. It was installed in what we called the mid-range units, and the choo-choo Trane, which are the pre-IntelliPACs. It featured supply fan control, compressor staging, failure alarms, temperature inputs, and airflow verification. The TIM allowed the Tracer100 to issue discrete commands and get real-time feedback from units using a defined input-output map that included points like compressor on-off, heat fail, dirty filter, supply air temp, zone temperature, and airflow. It was a foundational step in Trane's move towards centralized programmable control. Then came the TIME, or Tracer Interface Module Enhanced, which emulated thermostat logic to integrate third-party equipment into the Tracer100 on the standard thermostat terminals, R, G, Y1, W1, etc. Alongside the TIM, Trane developed the PCM, or Programmable Control Module, which was used for air handlers, climate changers, and generic input-output control. The PCM allowed the end user to create custom programs to control almost anything, and could be configured for a wide range of applications, making it a versatile tool in the early days of building automation. Together, the TIM and PCM represented Trane's first real push into distributed digital unitary control. The next series of units introduced were the smaller Precedent and Voyager units. These units split up unit control and communication into two different circuit boards. You had the Unitary Control Processor, or UCP board. The UCP was the brains of the unit, and can communicate out in two different ways, each requiring its own module. If you wanted to tie into the building automation system, you needed the TCI, or Tracer Communication Interface. If you wanted to use a conventional thermostat, you needed the CTI, or Conventional Thermostat Interface. These Voyager and Precedent units were the first Trane units to have the main supervisory control board connected to other application-specific satellite boards that all communicated back to the UCP using its own protocol. To master the UCP and its satellite boards, technicians relied on the Voyager Microcontrol Manual, the definitive reference covering every control board, every signal, and every terminal definition. As the 90s progressed, Trane introduced Tracer100. This system improved on the limitations of the Tracer100. Instead of a terminal monitor, you now had a dedicated PC with a Windows-based platform that brought true building automation to life. Tracer100 communicated with COM3 and COM4 networks tied into the building control unit, or BCU, which was the backbone of the system. You could seamlessly replace your Tracer100 with the new Tracer100 and communicate with the older existing controllers. For the first time, operators could view floor plans, alarm routing, and schedules graphically. They can visualize data, trend equipment performance, and manage multiple systems from one single interface. Tracer100 marked a shift from fully monitoring to a fully integrated building automation system. Tracer100 was also designed to be backwards compatible with the earlier COM3 and COM4 networks. But then Trane introduced a new generation of unit controls called ReliaTel. ReliaTel kept the same style of board-to-board intermodule communication that the Voyager units had pioneered, but it also expanded with three different communication interface boards. The first was the TCI-R, or Tracer Communication Interface, for COM3 and COM4 integration. The second was the LCI-R, or LonTalk Communication Interface, which opened the door to COM5 LonTalk integration. And then in later years, the BCI-R, or BACnet Communication Interface, gave ReliaTel units the ability to speak BACnet MSTP. This was the moment when Trane rooftop units began to bridge the gap between proprietary networks and open protocols. Even though ReliaTel offered the BCI-R board that spoke BACnet MSTP, Tracer100 itself could not directly communicate with MSTP networks. It could communicate with BACnet IP via Ethernet, but if you wanted to communicate with BACnet MSTP, you would need a BACnet IP gateway. When the HVAC industry was deciding which open protocol would be implemented across equipment, Trane initially backed LonTalk. It created the Trane proprietary COM5 controller platform, which was built around that LonTalk choice. But as the wider industry moved towards BACnet, Trane had to adapt, which led to the development of the new family of controllers designed with BACnet in mind. These were the UC controllers, each tailored for different applications. You had the UC210, which was for VAV boxes and small fan coil units. The UC400 provided advanced unit control with different profiles. The UC600 expanded capacity for larger systems. And then the UC800, which was the backbone for chillers and high tonnage equipment like IntelliPacks. Together, the UC line represented Trane's shift towards BACnet integration, while still maintaining compatibility with their legacy networks. As Trane moved into the 2000s and 2010s, the next major step was the introduction of the Tracer-SC, or system controller. The Tracer-SC replaced Tracer100 as the head-end platform. It moved away from the thick client software on a dedicated computer into a web-based interface. For the first time, operators could log in through a standard web browser to access the system and see schedules, alarms, and graphics without needing a dedicated workstation running specific software. The SC also brought native BACnet support, both MSTP and BACnet IP, while still providing gateways to legacy COM3, COM4, and LonTalk devices. Then in the 2020s came the SC Plus and its Synchrony platform, which refined this approach, giving users a cleaner, more modern experience with improved graphics and mobile access. But as Trane moved deeper into BACnet, it was clear that their controls needed to align more closely with the BACnet standard convention that the rest of the industry was adopting. Today we arrive in the Symbio era. Symbio 700 for rooftops, Symbio 800 for IntelliPacks and chillers, and the Symbio 500 for terminal units represents Trane's most modern generation of controls. Unlike earlier systems that relied only on a two-wire communication bus, the Symbio line is built around BACnet IP and Ethernet, giving it faster, more reliable communication and aligning it with the standards that the rest of the industry is using. These controllers speak BACnet natively without the need for external interface boards. They bring built-in diagnostics, mobile connectivity, and cloud readiness. Symbio reflects both the technological evolution of Trane's controls and the industry's demand for smarter integration, energy savings, and open communication protocols. This is the story of Trane's controllers through the ages, an evolution from simple switches to smart systems, from closed protocols to open standards, and from isolated units to fully integrated, energy-conscious building intelligence. What will be the next evolution in Trane's journey? Could AI be the answer?
Don't forget to like, comment, and share. This video took me a month to complete. Any help would be appreciated. Thanks for watching.